Okay, good morning, everyone. As so kindly introduced, my name is Richard Spears, and today I'm going to be talking to you about Twisted. Can I get a quick show of hands? How many people here have experience with Twisted at all? Okay, so a bit of a mix, half and half. Just a disclaimer, I'm not a Twisted guru, not a super expert in all this, but I think we do some pretty cool, interesting things with it. So hopefully after this talk, some of you can maybe take up some of our approaches or begin looking at Twisted for your own projects that require network capabilities. Okay, so starting off cloud. As we heard, this is quite a buzzword from the closing talk yesterday. We are basically from Oracle's cloud development team, and we're building an infrastructure as a service-based offering to power Oracle's various products, including their software as a service products or their platform as a service product. So the general idea is here that we're right at the bottom, we're powering the underlying infrastructure that they are then building on for some of their other stacks. Our team was formed with the acquisition of Nimbula. Some of you may know of Nimbula. It was a startup that Oracle acquired last year, and it was providing a private cloud solution to enterprises. Some of you may remember one or two talks given by some of our other team members like Bryn, who gave a talk on RESTful APIs at PyCon a while back. Okay, we're based in Cape Town. About half of our core development team is there. The other half is in California. We're still a pretty small team at the moment, but we are growing quite rapidly, and we're starting to add one or two developers in various locations around the world. We've recently got some guys from Canada joining the team. We're mainly a Python shop, hence attending and talking at PyCon. We do have some customized components in other languages such as C or Java for various reasons such as performance optimization, but by and large we code in Python. As we're building this distributed computing platform, we have a lot of different nodes, a lot of different services, and they're all communicating over a network. Hence, we are using Twisted to build these services, as we find it is very useful and easy as a library when working with network components. Okay, so on with the talk. This is a brief overview. I'm going to touch on asynchronous programming, then introduce Twisted and some of the concepts there, before talking on things that are more specialized to our environment, such as how we track context across our multiple services, our multiple nodes, as well as how we can monitor the event loop or the reactor to detect any stalls, and how we handle time jumps on some of our components. If there's time left, I will briefly cover on an approach we use in our testing to monkey patch for certain environments in a fairly clean way. Okay, so event-driven programming or asynchronous programming. On the left, you can see the traditional view. This is a single-thread programming model. You write code, and it flows from top to bottom, and it processes things as expected. You can see there are three different tasks, which are representing some sort of computation or operation, and it flows one after each other while waiting for certain things to complete. The white would be maybe it's waiting for some I/O to complete, reading a file, talking across the network, anything like that. In order to speed this up, you can try to follow a multi-threaded approach, which would be something like the middle picture. We are now spreading these computational pieces of code across more CPU cores. This is supposed to give you a speed increase. I'm not going to get into the whole debate about the Python GIL and whether or not you actually get an accurate speed up when you start doing threading systems in Python. However, this does have a drawback in that it introduces a lot of complexity in how you handle any sort of shared state or shared resources. If you have one thread that is updating a variable, you need to put some sort of locking mechanisms around that so your other threads don't try to update it at the same time. And normally you can, if you don't watch what you're doing, end up with very hard to debug race conditions, where normally your program works perfectly fine, but every now and then things go horribly wrong, and it can be quite hard to debug. The third approach is on the right. This is event-driven programming. You basically have a loop that is continually spinning, waiting for an event. And when that event happens or is triggered, it executes a particular bit of code. Normally we talk of things like event handlers or callbacks, and these are functions which are executed when something happens. Some examples of programs or libraries or programs developed with this event-driven programming approach. Twisted, the networking framework I'm speaking about today, it's written in Python. You have an event machine for Ruby, Node.js for JavaScript, and a good example is Nginx, which is a web server. Some advantages of why you would want to do this sort of event-driven programming approach. Firstly, it avoids polling. You don't have to continually say, are you done, are you done, are you done, or block and wait for something to finish. You can just have your code executed when that I/O is actually completed. So this scales very well for I/O-based workloads. You know, if you're writing a web server that is handling a lot of different connections and it has a lot of different I/O going on, it's a good approach to use. It's not necessarily the best if you are doing pure computational workloads, but most of the work we're involved with isn't bottlenecked on, it doesn't have a bottleneck on the processing side, but rather on the I/O side. Naturally, it's just better suited for some domains. Some domains that you are trying to solve a problem have periodic events or a framework that's already existing where you are programming an application to match that. You know, it has an event that occurs every 5 minutes, or you are waiting for other things to happen. There are some disadvantages for this. Firstly, the risk of some spaghetti code. Because you are now programming through these different event handlers, you can start jumping all over your code depending on what events are firing, and you can build quite a nasty, deep path for where you're jumping from event handler to event handler, and it gets hard to understand. You also, as it's a single threaded based approach, you have one main event loop. If you do some processing on that event loop incorrectly, you can block the event loop, which means you block your entire program and nothing else happens until that blocking code finishes executing. We'll see later on in my talk how we've added some monitoring to pick these sort of situations up. Okay, it can be harder to debug. As I said, you're no longer reading your source code from start to finish. You also will end up in an event handler, maybe not necessarily knowing exactly how you've got there, and you lose the call stack that you could normally follow to see, oh, this happened, this happened, this happened, and I'm now here. Normally, you just get a traceback saying you're here. It's more useful for languages that have first-class functions because you are, triggering these functions when various events happen. Okay, on to Twisted. This is a fairly mature project. I think its first stable release was in the early 2000s, so been around for 12 years, give or take. It has a lot of built-in libraries, a lot of functionality. It's been tested quite heavily, so it's quite a reliable component to include in your stack. Normally, you would be looking at Twisted because you want to build some sort of application that preferably will be able to handle multiple simultaneous connections over the network and still give a good responsive, have a good response when interacting with it. So, attractive qualities. Obviously, it's written in one of the best languages out there, Python, so that's a good start. It has very large protocol support. It has protocol support for TCP, UDP on your sort of lower levels, HTTP, SSH, DNS on your higher application levels. So it really is quite fully featured. It's cross-platform. Not only is it cross-platform, i.e. you can get it to run without errors on the platforms, they try to also use the most efficient mechanisms for the underlying platform. So whether this is something like ePOL on Linux or KQs on BSD or IOCP on Windows, they try to use the most efficient form for implementing this event loop. Your mileage may vary with some of those different reactors. The standard default ones are pretty well tested. It is very easy to extend. You want to implement a custom protocol that no one's ever built before. it's very easy to do that. It's designed to allow you to do these sort of things. It's also got an integration-friendly base. Quite often you can build services or components that are talking to each other. For example, you could build something that receives an email from one client, does some processing, and sends it out on IRC, for example, if you wanted to do that. The architecture of Twisted, it consists of three main components. You've got your reactor loop. This is the event loop. Your transports, which are connections between two endpoints, and the protocol, which is the actual implementation details for whatever protocol you're speaking. As mentioned, the reactor loop just waits for events. These events can be I/O, they can be time-based, etc. The transports would be your TCP, UDP, and they basically expose a write method, which is non-blocking. So you would call a write on your transport, and that would send it out over the network. Protocols are where the actual protocol details are implemented, and it exposes a data received event where you can process whatever data has been received. Okay, a quicker example. I wrote a very, very basic example just tying these three components together. And the basic idea here is I have a server listening. Whenever it receives any data, it just sends back a list of, one of the talks from the PyCon ZA list of talks. So when we have data received, just simply write on the transport, a string, and then drop the connection afterwards. That's a protocol. A protocol is basically representing a connection. So you would spin up an instance of a protocol for every connection. In order to do this or to share state between your different protocol instances, you have a protocol factory. As you can see, when this is initialized, it just reads that file which contains the talks, keeps it in a variable so it can be accessed by all the different protocol instances. And I'm taking a bit of a shortcut here. I'm saying protocol equals PyCon ZA server. This is a shortcut that Twisted allows you to do instead of implementing a build protocol method, which would normally return an instance of your protocol and do some initialization. But since that's such a common pattern, Twisted have built in support for shortening it just to that. So I'm just saying what protocol I'm using with this factory. Okay, to start the server listening, we just call listen TCP on port 8000. We give it the factory that we are using for establishing these connections, and then we start the event loop or start running the reactor. Client is just as simple. Once again, we are basing our client on Twisted's protocol class. We have a function for data received, which just prints out the data it has received. And whenever a connection is made, it just writes one talk, please. So here you can see I'm doing a very basic example, not doing any binary data processing. I'm just sending strings back and forth. Once again, nothing to the client factory. Here I'm actually doing something you probably wouldn't do in real life. Whenever I receive a connection lost, I'm just scheduling a call later in after 2 seconds to reconnect. This is purely so when you run this code, you just see a nice list of talks being returned. In real life, you would probably replace this client factory with a reconnecting client factory, which basically will implement exponential back-off time delay before attempting to reconnect. So if a connection drops, it will reconnect automatically. If it drops again, it will wait a while and it will back out its connection attempts so you don't overload whatever you're connecting to. But once again, you're literally changing client factory to reconnecting client factory, and you're getting a whole lot of that support built in without having to do anything. To connect to the server, we just call reactor.connect TCP. We give it the factory, and we start our event loop. So now we've got our client-server implementation complete in just a couple of lines of code. Also to note, the transports and protocols are completely decoupled. So in order to change this to run over SSL instead of just a plain TCP connection, it's maybe another 2-3 lines. You just change your connect TCP to be something like connect SSL. You pass in a context with your SSL certificate, etc., and there you're done. If you wanted to test this, you could replace the transport with some sort of text-based transport. So then instead of sending over the network, you're printing into a variable. You can basically end up with a log file of all your communication instead of sending it over the network. The decision to break the transporter and the protocol apart was a very good one, and it's proven to be very useful in the real world. So now that we've gone over all those basics, let's make things a little bit more complicated. Introducing deferreds. So now this basically is a representation of something that's going to have a result in the future. I'm going to call some IO operation right now, and it's going to return a value, but that value is representing something that hasn't happened yet. So why you would use this is normally it provides a good abstraction to manage your callback chain. So here I've got some operation that does some IO, just called it do some IO, and we will get a deferred returned. On that deferred, I'm going to add a callback with a success function, and I'm going to add an error back, well, I'll call add error back, which adds an error function to be called if that operation failed in some way. I'm not going to go into details of what exactly that means. Think if you throw exception or return a special value, etc. It decides if you call your success function or your error back function. So there are two different chains for successful processing and error processing, and you can jump between the two. So if this returns an error, it will go to the next callback one level down in your error chain. If you successfully manage to handle that error, you can jump back into your success chain. So there are always these two chains, they're always the same length, and you can hop between the two depending on what is actually happening in your operation. Now, that can get a bit confusing. If you're trying to figure out what this does, you can have a whole lot more of these, and you would have to look up each of these function definitions and jump around your code and try to piece together what's actually happening. So if you're new to Twisted, you can use this thing called inline callbacks, which is a quite magical decorator that allows you to program in a linear fashion. So previously, you would have something like search remote file. It would download the remote file when that was finished. It would move it to a temporary location, maybe search it for some data, and then clean it up and remove it. So I've added a callback for my ready function, adding callbacks for success or fail, and then adding a callback to clean up. So here I've done call both. So I've now got the same function that's in both of those chains, both a success and an error. This would normally be something like your finally in Python. You know, it's going to happen whether the operation succeeded or failed. So here you add your decorator, and basically you can now use this yield keyword to just operate as normal sequential programming. So this function is going to block until the deferred that would have been returned here is fired or triggered. So you don't have to start jumping around into different functions, different callbacks, handling error conditions. You can just write your function as normal, straight down, and it will take care of it for you in the background. When I said block, it doesn't actually block, it just switches to programming. I mean, another bit of code that's executing, and it will return to this when it is ready. Sure, okay, so a whirlwind introduction to the Twisted basics. Let's move on to what we do in terms of our monkey patching to fiddle around with some of these details. Firstly, tracking context. When I talk about context, I am basically saying, how do I know what actions go together? Or I've got an API request and I've performed 10 different actions on 10 different servers, and I want to tie that all into one unit. So I need to have a bit of idea of what's going on and how things are relating to each other. So with Twisted, you are continually doing this asynchronous programming, and you have these different requests coming in. So normally for our context, we want to save the current context, whatever we are currently working on, apply a new context that is related to the action we are changing to, do that action, and then fall back to the old context so we can continue finishing whatever we were working on previously. So we've built a fairly simple context class to represent this. We normally just use a globally unique ID as our context ID, so it's just a very long string. And this is a very simple class. There's basically just exposing methods to save that somewhere and retrieve it from somewhere. We've also implemented it with a context manager, so we can wrap our various functions. We can say, with this context, do this, and it'll take care of setting the old context, while setting the new context, performing the action, and then reverting to the old context. Okay, so now that we have this idea of context and we've got the basic implementation of it, how do we get that applied everywhere easily so that it is uniform and we don't have to worry about it anymore? So that leads to us our first bit of monkey patching. Firstly, we created our own class for deferred. We call it deferred with context, which is very simple. It just saves the current context and then calls the actual other initialization procedures. It overrides the callback to do the same, to save context, set the new context, fire the deferred, and then revert back to the old context. So we do the same thing for the error back, and here at the bottom, we're just saying replace twisted's deferred with our deferred with context. So this allows us to keep all of our fiddling around to a very centralized location and apply it cleanly without having to patch it all over the place. We also define a function called func with context, which is a wrapper for various functions that does the same thing. Sets context, or saves context, sets the context, executes the function, then reverts to the old context. Now, this would normally be used with some of those other function calls like the delayed calls in Twisted, the call later. In the example I showed earlier for delaying the connection by 2 seconds, I used a call later. So this implementation is something we would be using for that sort of situation. As you can see, we have a add context to reactor. So this is how we introduce our monkey patching. We call add context to reactor on whatever reactor we are using. And basically, we're replacing the reactor.calllater with calllater with context. So now that we've got this concept of context and we've wrapped some of the twisted internals in it, we can now add this context object to various requests. For example, when we send out a HTTP request to one of our services, we include the context ID as part of that request. On the receipt of that request, it decodes it, so it pulls it out of that, applies the context, performs some actions, and then reverts. We also pop it into AMQP messages. So when we're sending messages along using RabbitMQ, we can track this one request to our API that is now hitting multiple servers, multiple services, going over HTTP, going over AMQP, and at the end of it, we have one context ID that's associated with everything. So very importantly, this now allows us to log with context. So we can now log this. I haven't done anything too fancy here. We're basically using standard Python logging, and we've just overridden this log method with this extra variable which contains the context. Okay, so that's our context and how we've added that. But now we needed to look at how we can handle stalling the reactor. So if this event loop that you are relying on to always continually be running and executing fairly quickly, what happens if you accidentally block it? Or what happens if the underlying time on the node you are running jumps backwards? Say someone's reconfigured NTP, or they've accidentally done a time jump on that node, and now all your callators, which you said happen 5 seconds into the future, happen 10 seconds into the future, if they've jumped the time on the node back by 5 minutes, you're now going to have to wait for those 5 minutes and then 5 seconds. And that's not the situation we want. So we've done some things to improve that, and I'll get to that later. Back to the event loop. The general idea is you have 4 event and event process. That's sort of a generic paraphrasing of the event loop. But for Twisted, we actually have this thing called self.doIteration. There are several different reactors provided by Twisted. I'm not going to go into all of those, but those are just different ways for doing or reading from certain file descriptors or polling for events, etc. But there's some general ideas that apply to most of these. You've got a set of file descriptor instances, for example, that you can check for read events or for writability. You've got methods to add readers or writers on these. And finally, you've got the generic methods that actually do the write or do the read. And somewhere buried deep in one of the reactors, you'll find something like this: for selectables method, fdset in r do read, self.reads, etc. That's going to go through all of them and actually call do read, whatever that function is on them. So how do we patch the reactor to handle these time stalls or to handle when we have blocking code on this on this event loop? Firstly, you need a cool function name. So we called it patch reactor for time travel. Okay. Now it also detects blockages in the as a side effect. And in a more serious note, we patch these sort of generic things that I showed you in the previous slides. So your add reader, add writer, do iteration, these are the targets that we want to look at overriding or patching to introduce some new behavior. I'm not going to go into the implementation of this blocking I/O timer just yet, but basically what you need to take from the slide is I've overridden this add reader. It takes in a reader object, it calls monitor blocking on that object, and then returns whatever the old function was. So we're still operating as normal, we've just added a step in between which we modify that object. Similarly, we do exactly the same thing for add writer. And now this is the do iteration loop that we have created to replace Twisted's do iteration loop. I'm not going to go too far into the details here, but just basically realize that we are doing some time-based monitoring. We're taking sort of timestamps, calling reset to this class, and then we're actually doing the old iteration. So that's what Twisted's do iteration loop would normally do, and we're just wrapping it around with some timing. We then look at these timestamps, and if we detect, oh, hold on, I thought the current time was going to be 5 seconds because that's what we're polling on, but actually it's much higher. We call this reset timers function, and I'll get to that later. Also, if we detect that we've been in this do iteration loop for quite a while, we just say total I/O processing time blocked reactor for X seconds. So now we don't actually know what caused the problem there. We're just knowing our entire I/O processing was longer than we expected it to be. We have more accurate reporting in other functions that I'll get to. So onto the implementation of this blocking I/O timer. We called it a class, timed reader writer, takes in a reactor and log. And this is the monitor blocking call that we saw earlier. So it saves a reference to the original do read and do write functions. I'm not going to get too far into details of why we're doing it like this. Here we're using the weak reference library or implementation to handle cyclic references. With Python's traditional garbage collection, if you have an object A that has a reference to object B, and object B has a reference to object A, you're going to run into some problems when the reference counting garbage collection tries to handle that. So we're assuming here that this class is actually going to stick around for quite a while. So if possible, we're wanting to base the rest of the functions that we see later on the class methods rather than the instance methods. I've skipped some code, but basically if we determine that this object needs to be patched for do reads, we define these two things, do instance read, which is basically just doing the original do read, but wrapped in a time call. Same with the class read, it's also just doing the do read, wrapped in the time call, but we are seeing if we can get away with doing using the function definition from the class as opposed to the bound function on the instance. Not going to get too much into all of this, but basically if the class function and the instance function exist and they're the same, rather basis on the do class read. This is a little bit of jumping around to handle, make the garbage collection more efficient. So we then assign the do read this is the monkey patching, and we also add this monitored flag so that we don't do this whenever same object is added to this loop. And obviously we say asynchronous the same process followed for writes. Stuff coming in Python 3,
now that we've patched,
they've taken a lot of ideas and based it off of the Twisted implementation.
The do write, and the
that was one of
iteration loop.
We can implement something that allows us to monitor for blocking calls on the reactor, as well as handling these time jumps. And this is this time call function that we saw wrapping things earlier. Basically, it's just doing timing.
I've got no idea why Twisted doesn't use it. Several other notable projects
if we
don't as well, like
that the
Zookeeper,
time
and there have been patches proposed to these various open source libraries to do it, but I think people are a bit nervous of,
it took so many seconds
they've
while
had this working for 12 years, everything's great, and now we were going to patch a very low level part of it. I'd imagine that hopefully in the future all of these things will run off monotonic clocks, because it certainly we've encountered situations where that would be very great to have. So hopefully they will do that sometime in the future.
Which does a very similar thing, but here we're actually logging a little bit more in depth, so we can try and get a model and a function name, and we can do a delay call, block the reactor for X seconds.
Great. Okay.
We can't always prevent people from programming things.
Sorry, just a bit of company history.
We had
it's been running probably for at least 5-6 years.
Someone was doing
there's a lot of
system call
stuff that
on the main
going back to before
to copy
Twisted,
some data. Normally
pretty stable around release 12
was
now.
very
I'm not
small,
sure if
but in certain
I'm not up to date on what the latest
data
version
was
is.
very large.
But we were
so now
implementing these things back in
a whole
8
loop until this copying finished.
There's quite a bit of time going on here.
Without this, you would be, this service is a bit slow. Why is it slow? And all your time stamping in your logs and everything will just be shifted by, so many seconds because of the delayed.
Without using inline callbacks, you can get some very neat
you're actually getting warning messages in your log
from
saying,
an architectural point of view. You can
why is this happening?
Set it up very nicely. But
in terms of you have handling time jumps,
some new guys joining the team who might never programmed with event-driven programming before, it can be a lot to take in.
So
this shift,
we log
as well as handling deferreds and callbacks, all these sort of things. So I think it's a very nice tool to get people into programming, but maybe once you become a bit more knowledgeable, a bit more advanced, you'll start falling back to not using inline callbacks. Because also you can make mistakes using them. You have to make sure you're doing the appropriate yields at the correct places and those sort of things.
I'm not going into
so it's great for starting, but maybe you want to start looking at not using it as you get more advanced.
With you our implementation of the monkey patch class. Twisted does have a monkey patch class by itself. We've re-implemented our own for various reasons.
Cool.
We take a more all or nothing approach where they allow you to be slightly more selective. So the general idea is when you initialize this class, you're passing in the globals and the locals and a dictionary which represents whatever you want to patch. So there's original dictionary, patch dictionary, and context, and basically it's just saving these references. We've also implemented the enter and exit methods, so you can wrap it. You can say, with monkey patch of this, do these following actions, and then when that context or that scope exits, it unpatches your monkey patch going. So this allows you to implement very clean tests, because you can do this in your setup.
No, don't worry about it.
It's all good. To revert back to your previous stage. Why you want to do monkey patching in your testing? Normally either for configuration changes or to change things that you don't have available on your local system. With standard unit testing, you're normally mocking out various things, and with this you can start very cleanly overriding and patching things, and then not have to worry about running into side effects when you are finished with that monkey patching. So the patch basically just saves the original value. There's some helper functions I'm not showing here, get object value, set object value, etc. Unpatch does this, the opposite of that, so it just reverts back to whatever it was. And this is how you would use it. You create a patch dictionary, then whatever, module A, submodule, some value. You assign it a new value, do that for whatever you want to monkey patch. And then here you can just say with monkey patch, globals, locals, and the patch, perform your actions, and then when it exits, it'll revert this monkey patching. I think that's come roughly to the end of my time, so I'll say thank you, and are there any questions?